All right, let's get right into this explainer and uncover the invisible chemical warfare happening inside every single bottle of wine. I'm incredibly excited to guide you through this today because honestly, we're going to look at wine in a completely different way. We aren't just talking about basic tasting notes here, we're going deep into the actual biochemistry that determines whether a vintage becomes an absolute masterpiece or a total disaster.
To really set the stakes for our explainer today, picture this. You're pouring a perfect, vibrant glass of wine. You're anticipating these amazing fresh fruit and floral aromas, right? But instead, it looks like muddy water, and it smells strongly of potato skins, bruised apples, and nail polish remover. Yipes, this isn't just a bad vintage. This is a catastrophic chemical failure. This is exactly what we stand to lose if the winemaker fails to defend their liquid kingdom.
So here is our battle plan for today. First, the threat of oxygen. Second, we'll meet our enzymatic enemies. Third, we'll dive into the winemaker's defense arsenal. And finally, the sensory culprits and aromas.
Starting with Section 1, the threat of oxygen. Our primary antagonist. It's literally an element keeping us alive right now, yet it turns into an absolute destroyer the very second a grape is crushed.
Okay, let's lock down a quick definition to anchor our understanding. Oxidation in wine essentially happens through two main pathways. You've got this super fast biochemical pathway driven by enzymes right when the grapes are crushed into must. And then there's a slower chemical pathway that happens later on in the finished wine. But here is the absolute crucial point you need to remember. Once this oxidative reaction happens, it is entirely irreversible. You cannot unbruise an apple, and you absolutely cannot unoxidize a wine. Once those compounds are gone, no magic handful of antioxidants is going to bring them back.
So what actually happens? Well, these are the real casualties of oxidation. White wines lose those crisp, beautiful greenish hues and turn a muddy golden brown. Red wines lose their vibrant violet tones, shifting to this dull, brick-like orange. Those fresh, tropical fruit and floral aromas you love? Completely wiped out, replaced by the smell of cut apples, honey, and yeah, potato skins. And it even messes with the physical texture in your mouth. The wine will literally taste significantly drier, all because the phenolic compounds clump together and strip away that soft mouthfeel.
Moving on to Section 2, meet the enzymatic enemies. Because for this rapid biochemical oxidation to kick off, oxygen needs a catalyst.
We basically have two main culprits here, and they have very different threat levels. First up is tyrosinase. Think of tyrosinase as your common foot soldier. It's naturally hanging out in all healthy grapes, happily turning compounds into browning pigments. But the good news, it naturally fades out as the grape matures. By the end of fermentation, it's pretty much useless, and winemakers can easily knock it out with a tiny dose of sulfur dioxide. But then we have laccase. This is the elite boss. This enzyme is only brought in by gray rot or Botrytis cinerea. And let me tell you, laccase is a winemaker's absolute nightmare. It sits on the outside of the grape, washes easily into the juice, and stubbornly attacks a massive variety of compounds. Unlike our foot soldier, laccase completely survives fermentation and is incredibly resistant to basic defenses like sulfur dioxide.
And just to round out the enzymatic trio, we have peroxidases. But honestly, winemakers don't really lose sleep over these. They are for sure the weakest link. They technically live inside the grape cells, but they need a really high pH level to do their damage. Down at the normal, highly acidic pH levels of grape must, their activity drops off a cliff. They're practically harmless.
Section 3, the winemaker defense arsenal. So now that we know exactly who the enemy is, how in the world do winemakers fight back to protect the wine? Here is the overall defensive playbook. It's this awesome mix of physical and chemical tactics. The goals are simple. Keep oxygen far away, drop the temperatures to slow down reactions, maintain a low pH to keep those enzymes groggy, destroy the dangerous enzymes completely if you can, and finally, eliminate the fuel, the oxidizable polyphenols, before the enzymes can even spark a reaction. Let's zoom in on that last strategy, starving the enemy. By deploying specific agents, winemakers basically strip out the metals and phenols, taking away the fuel. Gentle pressing helps extract fewer of these compounds right off the bat. Then, you've got analogical charcoal acting like a massive sponge to pull out phenols, though you have to be careful not to strip the good flavors too. They even use synthetic polymers to absorb heavy metals like iron, which act as catalysts.
And this is wild. They actually use natural proteins like milk casein, or literally plant proteins extracted from peas and potatoes. It sounds crazy, but these potato and pea proteins act as natural sponges, soaking up the bad stuff and leaving the wine totally pristine.
Now, if you can't remove the fuel, you have to cut off the oxygen supply. And winemakers have an amazing trick for this. They use dead yeast cells. Seriously. After fermentation, they leave these dead cells, called lees, suspended in the tank. These little guys act as tiny oxygen sponges, naturally eating up dissolved oxygen before it hurts the wine. Winemakers also use inert gases, carbon dioxide, nitrogen, argon, to fill up the empty space at the top of the tank. It forms this heavy, invisible blanket that physically blocks out the 21% oxygen floating around in the air.
Then we get into the actual chemical warfare, chain blocking. When oxygen does slip past the defenses, winemakers use this incredible 1-2 punch. First, they drop in ascorbic acid, which is just vitamin C. It is highly reactive, so it bravely jumps right on the grenade, reacting with the oxygen and neutralizing those radicals to save the wine's delicate aromas. But there is a massive catch. When vitamin C takes that hit, it mutates into a brand new chemical that turns right around and attacks the wine. That's why step 2 is absolutely vital. A precise follow-up dose of sulfur dioxide cleans up the mess and neutralizes the byproducts of the vitamin C. You literally can never use ascorbic acid on its own.
But hey, the winemaker isn't fighting entirely alone here. The grape actually brings its own defensive troops to the battle. Glutathione is this natural tripeptide packed into the grape juice, and it starts neutralizing free radicals from minute 1. Tannins, yeah, the same stuff that gives red wine its structure, are also extremely powerful antioxidants. They lock up the oxidized compounds and pull the dangerous radicals entirely out of the system.
Finally, Section 4. Sensory culprits and aromas. Because despite all these incredible defenses, the inert gases, the plant proteins, the SO2, sometimes the enemy breaks through. And when they do, they leave a fingerprint. Meet the main offender here, ethanol, or acetaldehyde. This is the primary byproduct that just screams oxidation. If you've ever smelled sherry, that totally distinct bruised apple and walnut aroma, that's acetaldehyde. It forms when alcohols react with radicals and oxygen. And get this, it is so reactive that it actually accounts for up to 75% of the combined inactive SO2 in white wines. Basically, the more acetaldehyde a wine creates, the more SO2 the winemaker has to dump in just to keep the wine from falling apart.
But oxidation creates more than just bruised apple smells. It creates these compounds called esters and acetates. Check out this table from the source data. Look at ethyl acetate. When that hits around 15 to 20 milligrams per liter, it smells like harsh varnish or glue. It's a major flaw. But it's not all bad news. Other compounds, like isoamyl acetate, are intentionally cultivated by winemakers to give things like Chardonnay a pleasant little hint of banana or pear, or 2-phenylethyl acetate, which gives off gorgeous rose and honey notes. It's this razor-thin balancing act, right? A little bit adds amazing fruity complexity, but too much oxidation turns the whole thing into a massive flaw.
So we've covered the overarching threats, the specific enzymes, the wild defense strategies, and the chemical fingerprints left behind. Ultimately, understanding this complex biochemistry transforms every single sip into a profound appreciation for the masterful defense the winemaker deployed to get that liquid safely to you. So next time you detect a hint of bruised apple or banana in your glass, ask yourself, are you just smelling fruit, or are you smelling the remnants of an invisible chemical war? Thank you so much for joining me on this explainer. Keep exploring, and I'll see you next time.